if you look at page coloring, actually, see, the issue they talk about why they came up with the idea of page coloring is that when you have spatial locality, we are talking about spatial locality in virtual addresses, isn't it? Because the compiler produces virtual addresses, and we are saying the next virtual address in the data is going to be the next data item I'm going to access because it's an array, let's say. Okay. And next instruction I'm going to access is not going to be a branch. Therefore, I'm going to access the next instruction as per the code which is there. And because we bring in blocks of code into cache, the expectation is that they'll be in the cache and I can, get hits on that. Now, the problem with one of the problems that they faced was that consecutive virtual address blocks map into some arbitrary random physical address blocks, isn't it? Because we are doing page mapping, right? We do page table mapping, so they can get mapped into any part of the physical address. When there is such arbitrary mapping from virtual address to physical address, it is very much possible that, or at least it is not deterministic, that the adjacent virtual blocks will not be mapped to the same physical block. Okay, so what happens, you will be using two adjacent virtual blocks, let us say, for doing your execution. But both the virtual blocks get mapped in direct mapped cache to the same physical block. So they keep kicking each other out, which is exactly what is thrashing in paging, right? So that is a big problem and leads to very high miss rate and very bad loss of performance. So what did they do? If we go back to the figure, okay, if you see this figure, what they are doing is basically they are coloring the blocks of the cache or to be of different colors, okay, and then they also color the physical blocks and the virtual memory blocks such that adjacent virtual memory blocks do not get the same color as, do not get the same color, because if they get the same color, they will maybe, mapping to the same physical block. That is one problem. So they do this, that from when they map from virtual block to the physical block, they make sure the color matches. And that color is one of the colors of the cache. And adjacent virtual blocks do not map to the same colored physical block, so that they will not map to the same block in the cache. By this, they'll be able to avoid this problem. Okay, but if you read Linus Torvalds' answer in the link I posted, he says we don't do page coloring anymore because L1 caches use set associativity and not direct mapping anymore. So it doesn't make sense to do page coloring, because if they map into the same set, we use different blocks for mapping them. So therefore there cannot be a conflict, and they cannot kick each other out. So that is the logic for not implementing it in Linux. So yeah, I mean, it does seem interesting that you can get 90% hit rate in caches, but that's the sort of special locality that you are dealing with. That's one part. But what we will also see is when we move forward, that architectures have evolved to do a lot of different things to actually anticipate what code your program is going to, what instructions your program is going to execute. So they have a whole bunch of predictions, right? Prediction algorithms. Like I told you, some people have even been trying to use machine learning in operating systems, but maybe someday, if you have a machine learning processor or co-processor sort of a thing, they may want to do simple predictions using machine learning for architecture itself. But as of now itself, they do a lot of predictions which we will learn, and because of which the performance of the processor improves. Secondly, they do other tricks even if their prediction is wrong to keep the processor moving. So they try to minimize the number of stall cycles in the CPU, which is why your the running of the program is really very fast. Then, of course, there are compiler optimizations, some of which we will be studying today. Not today, next class. How the compiler optimizes your code to see that, the performance is really good. So all the various things, when you put them together, then it actually works that way. So in fact, in Linus Torvalds' answer, he says the reason that we can start the lookup of the L1 caches even before you even do the TLB lookup, and in fact, you want highly associative L1 caches to do that, he says. And so L1 caches are even 4-way associative is what he says. And so he uses the word O, which is basically for out of order execution that the newer architectures do, which is what we'll be studying when we come into pipelining and all. So such out of order execution processes are very good at hiding one cycle of latency. And so, in fact, my excitement about this was you can literally understand every word that Linus Torvalds writes if you finish, your chapter, at least up to chapter 3. So today, we'll be starting advanced cache optimizations. We saw 6 basic optimizations in the last 2 classes. Basic, the first 3 for reducing the miss rate are very simple. You increase the block size, increase the cache size, increase the associativity. Any of them would reduce the miss rate. However, increasing associativity or the cache size can increase hit time. And increasing block size will increase penalty, right? Miss penalty. So every optimization comes with some other element of the equation, the average memory access time equation affected probably. However, combining multiple things or trade-offs, we use trade-offs to say, okay, I can improve the miss penalty quite a lot, but not increase the hit time too much. Okay, then I would rather use it, right? That's a trade-off. Similarly, when I use high associativity, the power consumption goes up, the hit time goes up, but the miss rate comes down significantly. Now, when the miss rate comes down, right, the miss penalty is very less often invoked. Therefore, your overall average memory access time can become better. But the book has many examples where they show that even though associativity gives you better miss rate, it doesn't give you good average memory access time. And now, as far as advanced cache, okay, and so those were the 3 to reduce the miss rate. What were the other things we did to reduce the miss penalty? What did we do? What were the techniques to reduce miss penalty? We had 2 techniques we saw for reducing miss penalty. and one technique to reduce it down. What are the steps that are needed to determine when your processor requests for a word, let us say, at a specific address. So essentially, the processor is putting out the address. Now, this address is used to fetch information from the cache. What are the steps that are needed from the time the processor puts out the address to the word coming to the processor?
Mapping the virtual address to the physical address.
Okay, and then
Checking if the physical address is present in the cache where it is present.
how do you test that?
We match the set and then we check whether there's a tag. The tag value is present of the address.
So how do you get the set? Your address is divided into what parts?
Tag, set, and offset.
Okay, it's not called set, it's called index. Because it can be a set, it can be direct mapped cache also. Right? It's basically a tag, index, and offset. So you use the index bits to index into the cache, which will give you either the block in a direct mapped cache or the set in a associative cache. Then you do the matching of the tag, and then what? In the case of it, what's the next step?
We move the word from cache to the processor. Like,
how do you know where is the word? What's the word?
Offset is also given.
So you use the offset to go to the specific information in the block, and then you put it on the data bus to go to the processor. Okay. So that is the set of steps that are needed to move from the time the processor puts out the address to getting the data in its register. So that's what happens when you say load, essentially, right? When you say load something to the register, this is what is happening. Okay, so now we read 3 methods to reduce miss rate. Like I said, I shouldn't have said them. I should have asked you, but anyway, larger cache size, larger block size, higher set associativity. I'm asking you what are the mechanisms we learned to reduce miss penalty and to reduce hit time. Multi-level caches to reduce miss penalty, right? And the other one is to give priority to reads over writes. The write buffer thing, you remember, if there is a read miss, and it's a dirty block and it's a write back cache, we don't write to the memory, we write it to the write buffer, issue the read request, and then in the background do the write back. This reduces the miss penalty by half. Okay.